Welcome back to the massive open online course of MAT 522. In this last video, we will learn how to solve an LRC circuit. Similar to the spring mass system, solving an LRC circuit is exactly solving a second-order linear differential equation with constant coefficients. Therefore, in general, the solution to the charges on the capacitor at any time t is then given by Qt equals to Q of C plus Q of P, where Q of C is the complementary solution associated with the homogeneous equation. When the resistance R is non-zero, this part is also known as transient solution. On the other hand, Q of P is called the particular solution associated with the non-homogeneous term. When the electromotive force E is constant, then this solution is also known as steady state of the circuit. Since solving an LRC circuit, just like the spring mass system, is exactly solving a second-order linear differential equation with constant coefficient, we once again recall all the steps that we have learned in Chapter 4. First, we assume that the solution has the form y equals to exponent mx. Then, we construct the characteristic equation associated with the homogeneous part. Then, we solve the characteristic equation to obtain the complementary solution Q of C. Now, if the differential equation contains non-homogeneous term, then we proceed to find the particular solution Q of P via the undetermined coefficient with superposition principle. And then we combine both the complementary and particular solutions to form a general solution for the charges, that is Q. And finally, we solve any additional problems if given, such as initial conditions of the circuit, or etc. Now, we refer back to the same example number 1 from the previous video for demonstration. Recall that an LRC circuit has resistance of 20 ohms, an inductance of 2.5 henries, and a capacitance of 0.02 farad, with an applied voltage of E equals to 300 volts. Now, assuming that there is no initial current, but the initial charge is given by 2 columns. Find the equation of the charges on the capacitor at any time t. What happened to the charges after a long time? Now, this question now contains 2 problems. First, we need to find the equation of the charges. And second, we need to analyze and deduce what happened to the charges after a long time. Now, recall that we have previously modeled the second-order linear differential equation of this LRC circuit given by Q double prime plus 8Q prime plus 20Q equals to 120, subject to 2 initial conditions, Q of 0 equals to 2, Q prime 0 equals to 0. Now, let's proceed to solve this problem. Again, given the second-order linear differential equation, Q double prime plus 8Q prime plus 20Q equals to 120. Clearly, this is a non-homogeneous differential equation. And from here, we can find the characteristic equation associated with the homogeneous part, that is m squared plus 8m plus 20 equals to 0. This is a quadratic equation, and therefore we can find the root of this characteristic equation, and given the roots that we found to be complex, m equals to -4 plus minus of 2i. For the complex root, we have the complementary solution QC to be equals to exponent negative 4t in the big bracket C1 cos 2t plus C2 sine 2t. This is the complementary solution. Since given this second order linear differential equation is non-homogeneous, then we proceed to search for the particular solution. Given the non-homogeneous term GT happens to be 120, a constant unique value, by the undetermined coefficient with superposition, we initially have the particular solution Q of P to be constant A. And therefore, finding first and second derivative gives us Q prime of P equals to 0 and Q double prime of this P equals to 0. Now, substituting all these derivatives into the differential equation, Q double prime plus 8Q prime plus 20Q, this is equals to 0 plus 8 multiplied by 0 plus 20A. Upon simplification, we have 20A equals to the right-hand side of 120. Therefore, solving these linear equations, we have A equals to 6. And therefore, the particular solution, Q of P, which is equals to A, that is equals to 6. Combining both complementary and particular, we know that the equation of the charges QT is given by complementary plus particular solution, and therefore the general solution of the charges at any time t will be exponent negative 4t in the big bracket C1 cos 2t plus C2 sine 2t, and then plus 6. Now, this question also subject to two initial conditions, Q0 equals to 2 and Q prime 0 equals to 0. And therefore, we can proceed to solve this initial problem. Again, given by the equation of the charges to be exponent negative 4t in the bracket C1 cos 2t plus C2 sine 2t plus 6. So by the first initial condition, we have Q0 in which exponent 0 in the bracket C1 of cos 0 plus C2 of sine 0 plus 6. Upon simplification, sine 0 gives us value 0, exponent 0 equals to 1, and therefore this equation is 2 equals to C1 plus 6, the simplest form. Solving this constant, we have C1 equals to negative 4. In order for us to further finding the values of C2, we use the second initial condition Q prime 0 equals to 0. That is, we find the derivative of the equation of the charges. Q prime t using the product rule gives us negative 4 exponent of negative 4t in the big bracket C1 cos of 2t plus C2 sine 2t plus exponent of negative 4t in the big bracket negative 2 C1 sine 2t plus 2 C2 cos 2t. So this is the derivative of the equation of the charges. So again, by substituting t with 0, we have negative 4 exponent 0, C1 cos 0 plus C2 sine 0 plus exponent 0, negative 2 C1 sine of 0 plus 2C2 cos of 0. Using the same deduction, sine 0 gives us 0. So these two terms vanished. And that Q prime 0 equals to 0. This is just negative 4. Multiply. C1 we have found to be negative 4. Plus 1 multiplied by 2C, we have 2C. So in short, 16 plus 2C equals to 0. Upon solving again this linear equation, we have C2 constant to be negative 8. So finding these two constants, C1 and C2, we replace it into the equation of the charges. This gives us the particular unique solution. The charges on the capacitor is given by exponent negative 4t in the big bracket negative 4 cos 2t minus 8 sine 2t plus 6. And hence, we solved the first problem given in the question. Now, the last problem given in the question. After a long time, what happened to the charges? Now, based on the questions given, when the question mentioned after a long time, this means that t tends to go infinity. Now, from the equation of the charges that we obtained just now, once again, Q of t equals to exponent negative 4t in the big bracket negative 4 cos 2t minus 8 sine 2t and then plus 6. We have the condition after a long time when t goes to infinity, take note that exponent negative 4t tends to 0. This should be logical because exponent power negative 4t is equivalent to 1 over exponent 4t. As t grows bigger and bigger, 1 over a very large number tends to goes to 0. In other words, the equation of the charges qt will approximate to 0 plus 6, which gives us a constant number 6 in the end. In other words, the charges of the capacitor reaches a steady state of 6 coulombs after a long time t. Again, under this second questions, the key word here is after a long time. This can be represented by t approaches infinity. That's it for the solution of the LRC circuit, and hence end the chapter 5. Thank you for your attention. See you next time. Goodbye.